Okay, section 10.6 is on parametric equations. So I'm going to read what the book wrote. The set of continuous ordered pairs f of t, g of t form a plane curve where x equals f of t and y equals g of t are parametric equations. T is the parameter. Okay, so they're adding a third variable to the mix. The reason you might want to add a third variable to the mix is if you're tracking someone's location over time. Then you want to know their x and y coordinates, but you also want like a timestamp on what they're doing. Okay, they call it a plane curve, but it does not have to curve. So let me sketch, for example, what this might look like. Okay, the only thing that's really different is that it's going to have a direction. So it might actually curve. It might go like this. But to indicate its direction, we would put arrows. And that would indicate the points occurring as time passes. But again, even though it says curve, it does not actually have to curve. It could be a straight line that also has a direction depending on parameter t. Okay, so for example, when we're going to sketch the graph and we're going to indicate the orientation by making a table. So the first thing they tell me is x equals t squared minus 4 and y equals t over 2. And then they are restricting the domain of my t from -2 to 3 inclusive. So let me make a table. When I make my table, I'm going to plug in t, I'm going to get an x, and I'm also going to get a y. Okay, because they gave me a restriction on my t's, -2 to 3, I'm for sure going to plug in -2. I'm for sure going to plug in 3 so that my endpoints are clear because they're going to be closed circles. And I'm going to plug in a couple points between there. I'm going to plug in 0 and 2 because I have to divide by 2. So I'm going to pick even numbers. Okay, so to get my x value, x equals t squared minus 4. So if I do -2 squared, 4 minus 4 is 0. If I plug in 0 for t, 0 squared minus 4 is -4. 2 squared minus 4 is 0. 3 squared minus 4 is 5. Okay, now I'm going to plug the t into the y function. So y equals t divided by 2. So -2 divided by 2 is -1. 0 divided by 2 is 0. 2 divided by 2 is 1. 3 divided by 2 is 3/2 or 1.5 or something like that. Okay, now I'm going to go ahead and graph this. Now when I graph it, I'm still using the xy plane. So when I scale it, I'm going to think about my x values and my y values. Okay, what does this go to? X's go to -4 to 5. And my y values only go up to 1.5. Okay, I am going to graph the ordered pairs, but then I'm going to think about the direction afterwards. So my first ordered pair is 0, -1. My next ordered pair is -4, 0, 0, 1, and then 5, 1.5, so about up here. And those are endpoints at the ends because of the domain restriction from -2 to 3. So this is my curve that doesn't have to curve. It looks like this, okay, but because of the parameter t, there's a direction to this, so the order I plugged it in makes a difference. So from lowest t, from -2 to 0 to 2 to 3, I started with this point, then I went to this point, and I went to this point, and then I went to this point. So the direction on this is I started there, I went over here, and then I kept curving around this way till I got to the end point. Okay, technically you only have to have one arrow to indicate the orientation, but as I track the points, this is the order in which they're going, starting here at this endpoint, ending here at this endpoint. Okay, next we're going to practice switching back from parametric and rectangular equations. Okay, when it says eliminate the parameter, in this case, the parameter they're talking about is t, and writing rectangular equation form means they want only x and y in the equation. Okay, so for A, these are basically the two equations we started from. We graphed an example 1, except without the restriction. So to eliminate the parameter t, first I'm going to solve for t on one of these equations. I'm going to solve for t on the second equation because it looks easier. Okay, so if I solve for t, I get t equals times the 2. T equals 2y. Then I'm going to plug the 2y in for t in the first equation because this is going to eliminate the t. Okay, and then I'm going to simplify it a little. So 4y squared minus 4. You can leave it like that. If you want to put it in quote unquote standard form, you could add the 4 to the other side. But I've eliminated the parameter. There's no more t in the equation. It's only in xy form. And if I graph this, it would make this graph here, except without the domain restriction. The only problem is I have lost my direction. So without parameter t, I don't have a direction anymore, which is why we don't normally eliminate it unless we can figure it out without it. Let's do that same process with the next one. I'm going to eliminate the t so I can write it in rectangular form. Let's see, which equation looks easier to solve for t? I think I'm going to solve for t on the first equation because it looks a little nicer, or easier, I should say. If I want to solve for t, I can minus the 5 and I get t equals x minus 5. I'm going to plug that into the second equation where the t is. Okay, so I got y equals the square root of x minus 4, which does have a domain restriction, which I'm going to mention because we cannot square root negatives. So it must be true that x is greater or equal to 4. If I could have also gotten the domain restriction from the top equations as well. If I look at y equals the square root of t plus 1, according to that equation, it must be true that t is greater or equal to negative 1. Okay, because t is equal to x minus 5, then it also must be true that x minus 5 is greater or equal to negative 1. And then I would still get that x is greater or equal to 4 using these same equations. So either way, you're going to find the same domain restriction. Okay, for the next example, it says find the set of parametric equations using the given parameter for y equals 4x minus 3. So this is a rectangular equation. They want me to find parametric equations, meaning I'm going to have one equation that says x equals, one equation that says y equals, and because they're introducing the parameter t, it's going to be x equals something in terms of t and y equals something in terms of t. Okay, so for A, they have to introduce some direction on the parameter. In this case, they tell me that t equals x. Well, that means that x equals t is my first parametric equation. Now I'm trying to work with this equation right here. So I'm just going to plug x equals t into that equation over there. So I'm going to have y equals 4, and then instead of x, I'm going to substitute t minus 3. And then that's my parametric equation for y because now it's in terms of t. It's not always given in such a straightforward way. Okay, if it was not given as t equals x, it's something like this. Okay, I'm going to rearrange the equation and solve for x first. So let me see. If I solve for x, I'm going to add the x to the left side. So I get x plus t equals 5. So x equals 5 minus t. Okay, and that's going to be my first parametric equation. Now I've written x in terms of t. Okay, now I want to find the parametric equation for y. And I know that y equals 4x minus 3. So 4 for x, I substitute in my new parametric equation for x. Okay, and now my parametric equation for y is y equals negative 4t plus 17. Okay, now t is a common parameter to use in parametric equations, but another common parameter is to introduce an angle parameter. So we're going to, for example, we're going to sketch the graph of these parametric equations by eliminating the parameter. Okay, now when we do these, we use the Pythagorean identities that you remember from chapter 4 and 5. Okay, the easiest one to remember is that cosine squared plus sine squared equals 1. The other two, which we sometimes use, and sometimes there's more than one way to write it because it could be non-unique, is this one. The other one is this one. Okay, now let's look at this one right here. Okay, I have x equals 3 cosine theta, y equals 2 sine theta, and from 0 to theta, 0 to 2 pi for my theta, including 0, not including 2 pi. Okay, the first thing I'm going to do is I'm going to rearrange this equation and solve for cosine. So for the first equation, if I rearrange it, I could divide by 3 and I'll get cosine of theta equals x over 3. For the second equation, I'm going to solve for sine theta. I'm trying to create an equation using a rectangular equation using these parameters. Because I have cosine and sine, I'm going to use this identity because this is an equation I know to be true. So by plugging into this equation, it will create another true equation. Okay, because I found that cosine theta is equal to x over 3, then x over 3 squared plus y over 2 squared must equal to 1. Okay, I'm going to simplify this a little bit. Okay, and hopefully you recognize that this is going to be an ellipse. Okay, now I could graph the ellipse on its own without the parameter, but ultimately I am going to have to figure out the direction. So let me do a sketch of this graph. The center is 0, 0, the x radius is 3, the y radius is 2. Okay, this is a good graph representing this equation. However, there was a parameter and I need to respect the parameter. So I'm going to make a table with a couple points so I can figure out what direction this thing was going in. My parameter is theta. I'm going to see the x and the y. Now they told me my graph was going to go from 0 to 2 pi, which means the beginning of my rotation is 0. So let's see if I plug in 0. Okay, let me see what my x would be. My x is 3 times cosine of 0. The cosine of 0 is 1. So 3 times 1 gives me 3. I could calculate the y coordinate, but actually I already know x equals 3 is right here. So this is where I started. I could plug in the sine. I would get 3 times sine theta, which will give me a 0 here. But I'm just trying to get an idea of where I'm going. Now I want to pick another easy point. So probably I'm going to plug in pi over 2. I'm trying to go to see what happens as I go towards 2 pi. Okay, now if I plug in pi over 2, if I do 3 cosine pi over 2, the cosine of pi over 2 is 0, so that's going to be a 0. But I don't know if it's 0, 2 or 0, negative 2. So I need to figure out the y value. What is it? 2 sine pi over 2. The sine of pi over 2 is 1, so 2 times 1 is 2. So the next point this goes to is 0, 2. So from here, I'm traveling this direction, which is telling me the orientation of my curve. So this is the arrow I should be going in. Technically, I can just put one arrow, but if it's going that direction, it's going to keep going that direction all the way around the ellipse. And the direction is required if there is a parameter. Let's go ahead and try this next one. Okay, it's going to be the same idea. So I have x equals negative 1 plus tangent theta, y equals 2 plus 2 secant theta. For my theta, pi over 2 is less than theta is less than 3 pi over 2, which is not all the way from 0 to 2 pi, which is going to make me pause and think. But for the first equation, let me solve for tangent theta. So tangent theta equals x plus 1. For the second equation, let me solve for secant theta. Well, 2 secant theta equals y minus 2. So secant theta equals y minus 2 over 2. Okay, now let me check and see which trig identity has tangent and secant in it. So I'm going to use secant squared theta minus tangent squared theta equals 1, and that's because if I plug it into an equation I know to be true, it will produce another true equation. Okay, secant squared is going to be y minus 2 squared over 2 squared is 4. Tangent theta equals x plus 1. Okay, and I can tell this is going to be a hyperbola opening in the y direction. So I'm going to set it up and I'm going to think about it because that domain restriction is a little tricky. So my center is negative 1, 2. My x radius is only 1. My y radius is 2. So negative 1, 2. X radius is 1. Y radius is 2. I'm going to get ready to graph it though, so that once I figure out the missing information, I can just draw it. Okay, and this is going to open in the y direction, so because of this restriction, it's most likely going to be either up here or down here, but not both because it's not going all the way from 0 to 2 pi. So I'm going to make a table with the extra parameter theta to help me figure out the direction. Okay, now I can go from pi over 2 to 3 pi over 2 for theta. Let me think about this. Pi over 2 to 3 pi over 2 is this half of the circle, but I can't actually equal pi over 2, so I can't plug in pi over 2, even though I'm very tempted to. So what's another? Let me use this point because this is a nice point on the circle. This would be 3 pi over 4. So I'm going to plug 3 pi over 4 into the equation and see if that can help me get started. Okay, let's see. X equals negative 1 plus tangent 3 pi over 4. Negative 1 plus, what is the tangent of 3 pi over 4? This is negative root 2 over 2 comma root 2 over 2. Y over x is negative 1. So negative 1 plus negative 1 is negative 2. So I know, let's see, if I go to x is negative 2, well, that could be down here, that could be up here. I'm not sure which one that's going to be. Let me see what happens when I plug it into the y equation. Y equals 2 plus 2 times the secant of 3 pi over 4. That's 2 plus 2 times, what's the secant of 3 pi over 4? Cosine of 3 pi over 4 is negative root 2 over 2. Reciprocal, that's a lot of work. I think I'm not going to use that one. Let me try another point. Okay, so if I start here and go here, I tried 3 pi over 4. I got the x value, I just don't feel like finding the y value. So let's go over maybe to here, because that's another nice point to plug in. Let's try to plug in pi and see if we have easier work of it, because I'm just trying to figure out the direction. Okay, now if I plug pi into the x equation, x equals negative 1 plus the tangent of pi. Okay, what is the tangent of pi? This point is negative 1, 0. Y divided by x is 0 divided by 1. So negative 1 plus 0 is negative 1. Let me try the y and see if I get better luck this time. 2 plus 2 secant pi. Okay, what is secant is the reciprocal of cosine. What's the cosine of pi? That's negative 1. So the reciprocal of negative 1 is still negative 1. So 2 plus 2 times negative 1 is 0. Okay, that's a little better. Where is negative 1, 0? Negative 1, 0 is right here, which means I'm actually dealing with the bottom half of the hyperbola. So actually that gave me a lot of information. Okay, which is great, but I also need the direction, and I was kind of using these 2 points to figure out the direction. So at 3 pi over 4, because this is where I'm going from 3 pi over 4 towards pi, and I'm going to keep going after that. 3 pi over 4 to pi, I went from x equals negative 2 to x equals negative 1. this is x equals -1. X equals -2 is down here somewhere. So if I'm traveling from x equals -2 to x equals -1 along this curve, -2 to -1, I'm going this direction, which I'm going to mark on my graph. So I'm going -2 to -1, which is this direction, which means along this entire curve, that's the direction I'm going in. Technically, I only need one arrow. I'll put a couple so you can tell that I'm going to keep going that direction. Okay, and just like I did, you kind of just guess and check until you find convenient numbers that help you track what you need to do. Okay, last example, which won't be a bad one. This says find a set of parametric equations to represent this equation. Because I'm going to introduce the parameter of an angle, I'm going to use one of those trig identities. So I just kind of want to look and see what this resembles. Because it's something squared plus something squared equals 1, I'm going to go with cosine squared theta plus sine squared theta equals 1, although you could flip this. It could be sine squared plus cosine squared equals 1. There's more than one way to represent this. Okay, but if I go with this one, if this is representing cosine squared, then I'm going to think about what cosine must equal to. Okay, so if that is squared, then cosine must be x minus 6 over 10 because 10 squared is 100. Okay, and then I just want to rearrange this so I can solve for x. So I'll multiply the 10 to the other side. So x minus 6 equals 10 cosine theta, and x equals 6 plus 10 cosine theta. Keeping in mind this is not unique and there's more than one way to do this. Okay, now let me look at sine squared theta. I'm assuming that this represents this. Which if that's the case, then the sine of theta is equal to y plus 5 over 7, because that's what was squared. And then I'm just going to rearrange this so I can solve. So y plus 5 equals 7 sine theta. And then y equals -5 plus 7 sine theta. Okay, and those are my two parametric equations. And again, there's more than one way to do it. So you could have a different answer that's also correct.